So, with a typical ketone, we have, under what I basically had done yesterday, and that is sort of acidic mechanisms where protonation plays a role, we have one set that doesn't really play like that, and that is nitrogen nucleophiles. The reason for that is this is a reasonably good nucleophile on its own. You could draw protonation first or draw nucleophilic addition first. It really doesn't matter. Most books actually choose to take the nucleophile coming in without the assistance of the proton at this time. It's worth remembering, as with all of these things, that there are other equilibria going on that just are not productive. So protonation of the ketone is going on. Protonation of the nitrogen is going on. It just doesn't take us anywhere useful. So it's not that those are magically not occurring here. They are happening. They're just not going anywhere useful. So as with all the direct nucleophilic additions, we end up with an anionic oxygen, and in this case, a cationic nitrogen. We're in acidic media, so we're talking about having a proton source there to help us out with this. It's probably going to be relatively strong because part of this mechanism is the loss of water. So we're not going to have something that's going to be largely aqueous. So we're probably looking at a sulfonic acid or sulfuric acid, something like that. For our purposes, we'll just leave it as a sulfonic because that's most likely the candidate. So we're going to end up protonating the oxygen relatively fast. We're also at some point going to end up deprotonating the nitrogen to get this neutral. Any number of different things can do that, but one thing that we're not going to see in this type of reaction is a strong base, except for transiently this one. So it's not going to be there for long. Probably we're going to be talking about another molecule of the amine, if I had to bet on it, since that's more basic than an oxygen would be, which takes us here. All of these steps, and basically anything that we deal with that is acid catalyzed or acid promoted, are generally reversible. So don't get the idea that this is a one-way street. It is not. Generally, we have to work a little harder at things that are reversible because they're fighting back. We're still under acidic conditions, so we still have something that's available to protonate that oxygen. Now we have an oxygen that is potentially a leaving group. It is very rare that we will use hydroxide directly as a leaving group. It is impossible that we will use hydroxide ever as a leaving group in an acidic reaction. So we have an internal pair of electrons. What we're going to see is something very similar to what we did yesterday with the hemiacetal, and that is we're going to displace water. Only this time we're going to do it with nitrogen. Now we have formally water in the reaction, so we can use that in the next step if we want. That takes us here. This is an imine with an I. Imines have a very large role to play later on when we have to make amines with an A, since all we have to do here is something similar to sodium borohydride reduction of a ketone. We just have to reduce out a pi bond between carbon and nitrogen, and we'll have amines. That is, in fact, the best way of actually making them. We're not going to go there yet. There's a whole chapter on that later on. We're going to save that for then. But thinking parallel to what we did with a C double bonded O, you can see similar things that could be possible, at least, with a C double bonded N. In fact, they are very similar, except for the fact C double bond N is a little harder to work with. Why? Why do you think that would be the case? Why do you think that's a little bit more difficult to take out the double bond than that is? What's the difference? Basic conditions, strong nucleophile, so that H has nothing to do with it. What's the difference between O and N? Start with first principles. Slightly difference in size, irrelevant here. They're different in electronegativity. The reagents we're using to hit that carbonyl are taking advantage of the fact that the carbon there is highly positive because being attached to a more electronegative oxygen. Nitrogen is less electronegative, so it's not as polarized. So the carbon's not quite as interested. It still is, just not as much. So we're going to have slightly different reagents for it, but there are going to be some rate differences we have to think about in the long run. Overall, this is a very favorable equilibrium. Why? I've drawn it as reversible, but generally it lies heavily towards that product. Why? The trade-off point is the difference between reversing this, throwing the nitrogen out, or going forward by throwing the oxygen out. Why would it favor losing the oxygen? Ammonia was a neutral compound, stable. Water is a neutral compound, stable. So in those conditions, they're both reasonably acceptable as leaving groups. Why would it be heavily favored towards the forward direction here? We could even go so far as to make it very blunt. Why is water a better leaving group than ammonia? Back to first principles again. Why is the oxygen going to be more readily displaced than the nitrogen? Because it's more electronegative. It's already more polarized once it's protonated. So it's easier to get rid of. This, losing the oxygen, is actually easier to do than the reverse step here, which means this equilibrium will slowly drive towards the right. This is not nearly as difficult of a reaction to accomplish as making an acetal, where you have an oxygen nucleophile and an oxygen leaving group. You have no real electronic win there. So you have to play statistics games with numbers. Here you have an electronic win. You're losing a more electronegative group and replacing it with a less electronegative group. That tends to be a little bit better energetically. We could have done this process all the way through with a primary amine. So I could have used any alkyl, even potentially an aryl amine, as long as I had those two hydrogens, because they are lost as we go through. One of them is lost here. The other is lost here. The overall, one oxygen lost, two hydrogens lost from the nitrogen, overall, a loss of water. So I can have the third thing be carbon group or another hydrogen. Wouldn't matter. Mechanistically. Sterically, it might be a problem if we have a large, bulky ketone or something, but mechanistically, it wouldn't change things if that were an ethyl group instead of a hydrogen as the third attachment to the nitrogen. What if I replace two of them? if I did the same reaction setup with, just make it simple, ethylamine, I would end up eventually with a substituted imine, like that. I'm just replacing one of those H's with an ethyl group all the way through. What happens if I start with diethylamine? Under those same conditions. Well, to a point, it doesn't make any difference. We're going to follow exactly what happens up above until we get right here. And then we have a problem. We have no hydrogen that we can remove to make a neutral imine. That's a problem. So what happens instead? We can look at this as a resonance structure, and we're going to have a full cation on the carbon. Which is going to have some pretty drastic effects to its next door neighboring hydrogen that makes them a lot more acidic. So it's not going to take a great base to draw this. We don't normally draw the resonance form of this, but if you think of it that way sometimes, actually fairly often, it helps you see why something might be a problem or might be causing reactivity. So this is an unlikely resonance form, but still, it gives us a reason why these are significantly more acidic than usual. This is the first time you're going to see something that we're going to spend an entire chapter on once we finish the carboxylic acids, and that is removal of hydrogens next door. Alpha substitute, well, in this case, removal of an alpha hydrogen. The point of that, though, is it gives us the ability to replace that alpha hydrogen with something else, which is called alpha substitution. Right now, we're not going to go there. This is an enamine. Up to a point, it does exactly the same mechanism. But you can't get to a neutral imine this way. We don't finish our work with ionic compounds. We finish with neutral compounds. So if you can't make a neutral compound, then you have a dead end. In this case, you can make a neutral compound. It's just of a different form than what happens with a less substituted amine. Okay. Take it a step further. What happens if I put this together? Triethylamine. The answer is nothing. Hypothetically, it could come in as a nucleophile, but remember, it is now very, very sterically encumbered. It has 3 separate alkyl groups hanging off of your atom that's going to be your nucleophile. not happening. It'll chew up the hydrogen, so it'll act as a base. Now, why am I showing you dead ends? Does that just make me happy as an organic chemist to trick people? No, it doesn't. I'm showing you something very important for later. We use nitrogen compounds as bases very, very often, but we never use primary ones. We never use secondary ones because they are reasonably good as nucleophiles. We use tertiary ones all the time because they cannot act as nucleophiles. Even if they could get there, getting past the nitrogen addition step, there's no way to neutralize it, so it really only can go back to a neutral compound by throwing the nitrogen back out. So even if it could get to that carbonyl oxygen, it can't get anywhere productive because there's no way to neutralize the charge on it if it did. So we'll use this many times later on. This is triethylamine, a very common base, generally very useful, possibly because it's, well, very useful because it's a tertiary amine, meaning 3 alkyl groups on the nitrogen. It also tends to have a relatively low boiling point, so when you're done with the reaction, getting rid of it's not so hard, if there's any of it left. So when we get to that, and when we talk about bases, which we'll do before we get to the amine chapter, keep that in mind, that we don't use, by and large, ammonia, primary amines, or secondary amines in and of themselves as bases for our reactions, because potentially they act as reasonable nucleophiles. Tertiary amines or aromatic amines we get away with because they can't act as nucleophiles. There's no way for them to neutralize a charge if they did. So they won't.